Hello students, let's go for the next topic. Let's go for share screen. Okay, now let me go to electropotential. Okay, let's do it. Potential energy, the symbol is U, can be defined only for conservative forces. Remember from the previous class, we know that we have three conservative forces in classical physics. We have gravitational force, electrostatic force, and we have the extreme force. Three forces that are conservative forces. These are special ones because, as mentioned in this statement, potential energy is defined only for conservative forces. Okay, let's continue. Imagine that we have two masses, M1 and M2. Of course, the distance r from each other. Of course, exists a force between these two forces, and it's an attractive force, correct? And it's found according to Isaac Newton, right? That the force between these two objects is equals to a constant g, the universal gravitational constant, times m1 times m2 divided by the distance between the two masses squared. Correct, this is the universal gravitational law from Isaac Newton. Okay, as you can see, this is very similar to Coulomb's law when we have 2-point charges. This is for 2-point masses. Okay, now imagine that we have the ground. We're dealing now with gravity at the ground, correct? We have the gravitational field, the symbol is G, correct? Imagine that we have M at this position. Of course, there is a force, the gravitational force acting downward. Imagine that this position is YA at point A, correct? Later, we release it and it's acting by, affected by the gravitational force, and it moves to the second position, position B, correct? And that position is YB. Okay. Also, we know that according to Newton's second law, force equals to mass times acceleration. In this case, when we're dealing with gravity, the acceleration is just g, right? The gravitational field. From here, we solve for g, and g is equals to force divided by the mass. As you can see, this is very similar to the electric field. The electric field is equals to the force, the electrostatic force divided by the charge. In this case, the gravitational field is equals to the gravitational force divided by the mass. They're very similar. Why? Because the forces acting in these two cases is a conservative force. Okay, perfect. Now let's find the work done by gravity when we release an object from one instant. When we release it, and what happens being accelerated, right? So in this case, gravity is doing work. And by definition, work equals to force times displacement times cosine theta. That's the definition for work. Okay, now we substitute the values. Force done by gravity is mg. In this case, we're looking for magnitudes only. And delta y is initial. In this case, is delta y is gonna be this, the magnitude is this distance, right? And this distance is YA minus YB, correct? And when we multiply these two quantities, what do we have? The work done by gravity is equals to mg YA minus mg YB. Now let's define this quantity mgy as gravitational potential energy, correct? And substitute this value in the previous equation. What do we have? The work done by gravity is equals to the gravitational potential energy at A minus gravitational potential energy at point B. Also, we can switch these values to use the concept of change. It's easier, correct? And that way, this becomes negative, and At the end, we have that the work done by Bob is equals to negative the change of the gravitational potential energy. Let's do the same thing using the electric field. Okay, in this case, we need to create a constant electric field. Like in this case, right, the gravitational field by the ground, by the surface of the Earth is constant. Let's create something like that using the electric field. Great. To that, we have a very large a sheet, right, plane, which is charged. It has this density sigma. Remember, sigma is equals to charge divided by the area. And we create a constant electric field in the way we create a constant gravitational field. Okay, for simplicity, let's add another plate. These are a large plate, right, with opposite charge. In this case, opposite charge density, negative. Okay, great. And the same thing, let's use the charge, positive charge. Remember, by convention, at the beginning, it was believed that the charge that moves is the positive charge, not the negative charge. That's why we always, in this analysis, we take positive charges, because that was the convention, right? Because it behaves in the same way as the masses. If we have a positive charge right here and we release it, right, it goes downward in the same way as any mass released in the gravitational field. Correct? Like in this case, let's place this positive charge at point A, right? And of course, force is acting, the electrostatic force, and the position is RA. Later, when we release this charge, it's gonna be at position B, right, at RP. Perfect. And the difference in the distance between these 2 points is D. Right now, when we use the Coulomb's law that it was found before, right, the electrostatic force is equals to K times the absolute value of the charges, the product of the charges, divided by the distance squared between the 2 points. And that's the Coulomb's law. Great, for point charges. Now let's apply the definition of work. Again, it's gonna be, in this case, the electrostatic force times displacement in the y direction. We call it delta R times cosine theta. But what is the angle? The angle between displacement goes from here to here, and the force is going downward, right? In that case, the angle is 0, right? When we applied that angle in this equation, cosine 0 is equals to 1. And then what do we have? Well, also we substitute the value for the force, electrostatic force, and the value for change in R in this way. Actually, this change in R is the magnitude, right? It's this distance, it's gonna be RA minus RB. It's not the change actually, right? It's gonna be just the distance, the magnitude. Later we're looking for, we're using the meaning of the change. Okay, and then what do we have? When we multiply these two quantities, we have this arrangement right here. And then let's factor these two quantities, and what do we have? K Q1 Q2 over R minus K Q1 Q2 over R, but this is gonna be RA RB, okay? Because look, this is cancelled with this one, we have only one RA, and right here we have one RB. Something will happen, so I forgot to put these positions, okay? And then defining the same thing as we did right here for gravitational potential energy, we define this quantity. You can see these two are very similar. Look, this and these two are very similar. Correct? We define this term in general to be K Q1 Q2 over R as the electric potential energy. Correct? The electric potential energy. We define in that way. When we substitute this value, correct, in this equation, what do we have? We have the work done by the electric field is equals to the electric potential energy at point A minus electric potential energy at point B. Perfect. From here, we arrange it again to have or to use the definition of change, right? And I remember change is always final minus initial position, correct? In this case, what do we have? That the work done by the electric field is equals to negative the change in the electric potential energy. You can see they have the same form as right? The gravitational potential energy, the work done by the gravitational gravitational field, the same thing as the work done by the electric field. They have the same form. Why? Again, because the force acting in these two cases is a conservative force. Perfect. Now, one more time, this is the electric field. Now let's use the case when we have a continuous object, right? Like a continuous distribution of a charge in an object, correct? And the same thing when we apply the definition of work done, right? Now in this case, we use the electric field. In this case, we're using Coulomb's law. Now let's use the electric field, correct? So we solve for the electric force and plug it right here, right? And what do we have? We have that the work done by the electric field is equals to the test charge. This is test charge right here, electric field times the distance. This case are A minus that quantity at point B. Correct. Again, we defined the electric potential. Energy equals to Q naught, the electric field times R. When we substitute the value on the previous equation, what do we have? That the work done by the electric field is equals to the negative, the change in the electric potential energy. Again, we have the same form, but these are a little bit different because this is using the electric field. Again, they're the same, okay? They're the same, but right here, again, we use the electric field, and this is the definition of the electric potential energy, and right here, we use the Coulomb's law. Okay, perfect. Now, what else do we have? It says taking this difference to V equals to D. We have also that we can represent it. They were done by the electric field is equals to the charge, in this case, the test charge times the electric field times the distance traveled by the particle, the charged particle. Okay, great. And let's see. I remember by convention, we are using the positive charge to be the charge in motion, right? And now let's compare this charge to the mass. When we have a mass and we increase the potential energy and we release it, right? The mass is moving down or we're moving to the lower potential energy, right? And we have potential is converting to kinetic. The same thing happens right here, right? We have this charge on this electric field, which is constant, more or less constant, correct? And when we release the charge at this position where the charge is being accelerated, and if we compare this to the masses always move, right, from high potential to low potential. This simply happens to the charge. The charge moves from high potential to low potential energy, correct? In this case, we can take, in many cases, we take this to be zero potential, like when we're dealing right here in the horizontal plane, right? We take this zero potential, and when we increase the height, it's gonna be increases in potential, right? Gravitational potential energy. The same thing happens right here. We can take, right, this part to be zero potential. Remember, potential energy can be placed wherever you want. You can select your zero. Well, you can select the zero wherever you want, right? Like right here, we select the zero gravitational potential energy to be the surface, plane surface, right? Right. The same thing happens to electric potential energy, correct? We can place this or give the value of zero to simplify calculations. And of course, when we increase the distance to the positive charges, the electric potential energy increases. the same thing happens using mass, right? The gravitational potential energy increases when we increase the height. Okay, great. We know in the previous chapter that this is the electric field for a positive charge. Correct. Now imagine that we're moving this charge from one test charge from one point to another point. We take any path, right? This is a general motion. Usually we use path parallel to the electric field, but imagine there's a different path. Okay, and well, it's right here, and light is moving at this position 2 or position B. Is it position A, position B? And now let's try to take a small segment of the path, and let's take this segment tangent to the path to V delta L. We can take as a vector, right? And along the electric field, right? The distance we take it R, or the vector R, position R, right? And we have this change in R that has an angle, and we create a right triangle. Okay, and then what do we have? Well, this is the final position. Correct. This is at the same distance from the charge. We create this spherical path, or a circular path. We are in 2D, and we label this as RB, or position B, and this is the initial position also. We make a circular path, correct, and the radius is RA. We can use the integral. This is when we use calculus, but we don't worry about calculus. We just algebra. So let's use the definition of work one more time. It's force delta L times cosine. In this case, phi is the angle, correct? And cosine phi, according to this triangle, is equals to delta R over delta L. And from here we can define, right, that delta R is equals to cosine phi times delta L, right? Which is this part right here, right? Delta L cosine phi is just what? Delta R. Perfect. And what do we have? The work done by the electric field in moving a test charge from position A to position B is equals to force times delta R. So that's a matter of the path, right? Depends on the distance parallel to the electric field, right? On this distance, delta R is gonna be this distance, gonna be not this distance from here to here. At the end, gonna be only from this line to this line, delta R. Correct? Perfect. And then we use Coulomb's law. Remember, it's equals to Q naught divided by 4 pi epsilon naught R squared times this difference, because this delta R is RB minus RA, correct? And what do we have? This is equals to negative this product, correct? Perfect. Actually, we have negative at the beginning. Okay, perfect. And then what do we have? We have that, again, taking the electric potential energy. This is a definition, Q naught over 4 pi R epsilon naught times R, right? Because we have this R right here. What do we have? We have that here, that the work done from A to B is equals to negative the change in the electric potential energy. And this is the definition, another definition for electric potential energy. Remember, before we use when we have the electric field. Now when we use Coulomb's law, correct? Perfect. And look, when we're looking for more charges, when we're using more charges, only one charge. When we use more charges, right? The electric potential energy is equals to this product times the sum, right, of Q sub I and R sub I, right? This ratio. That's the work done on Q naught moving in a field caused by several point charge. Right here we have only one. We have to see we have 5, 6, and we are doing the same process, right? Moving the charge from here to here. Well, now we have to take into account the rest of the charges. We have examples later. Okay, and this is a case when we have bringing charges from infinity to some position right close to this charge, right? We have more charges, bringing charges close to this charge, and we have to do work. Or imagine that charge are positive, right? Remember, positive repel. So we are taking a charge from far away distance closer to another positive charge, both are positive, and they repel. So we have to do work against the field, against the electric field. And the work done on bringing charges from infinity to their final position is defined in this way. Correct? Perfect. We have examples later. Great. And then we have potential energy is always defined relative to some reference point where potential energy equals to 0. Like in this case, where is potential energy equals to 0 at infinity? At infinity, the distance, right? The distance is each distance of the whole term, the whole quantity approaches to 0. Correct? And that's the when we have point charges. That is our 0 potential energy. When we have object like before, right? We have two plates. Usually, these are not point charges, are plate. They have we have a charge distribution, correct? But in this case, we have to take one. Usually, we take one to be 0. The negative one is 0. Correct? Perfect. Okay, now let's look for some graphs. Correct. Using let's see how the electric potential energy changes with distance. Right, that's the behavior. This is when potential energy, electric potential energy is positive, and that happens when both charges have the same sign. Could be positive and positive, and negative. Correct. When they're opposite, right? They have opposite charge. Well, this is gonna be the curve of the electric potential energy. Correct, in that way. Again, the product is negative, correct? It's less than 0 or negative. It's the same meaning. Perfect. Now let's go to the electric potential. Yes. The potential energy of the system per unit charge Q naught is independent of the value of Q naught and has a unique value in the electric field. Let's see it. This is the definition for the electric potential, right? Electric potential is just potential energy divided by the charge. Remember, every time we have a quantity and we divide that quantity by another quantity, we create a new quantity and we have to define it. Like in this case, we have this quantity, electric potential energy, and we divide it by another quantity, the charge, electric charge of the test charge. So we create a new quantity and we have to define it. And we define that as the electric potential. Okay, perfect. And this is the electric potential or just potential. And the unit is volt. And 1 volt is equals to 1 joule, in this case divided by 1 coulomb. Correct? 1 joule divided by 1 coulomb is 1 volt. Again, when we substitute the values for the electric potential energy, we get that the electric potential is just the charge divided by 4 pi epsilon naught times R. Correct? This is the electric potential due to a point charge. This is for point charges, this formula. Okay, and this is when we have a collection of charges, right? to find the total potential energy produced by a bunch of charges, what is gonna be 1/4 pi epsilon naught times, right, the sum of the Qi over Ri, correct? Perfect. And now let's go for the change, right? Or potential difference. This is a change in the electric potential or potential difference. This is actually called voltage. The potential difference is voltage. It's defined as a change in the electric potential energy divided by the charge. Right? The change in electric potential energy equals to negative work done, right? Moving a done by the field, the electric field, moving a point charge from point A to point B and divided by the point charge. Correct. Going back to the values for work using the definition, dealing with the electric field is equals to this. At the end, what do we have? That the potential difference, right, is equals to a negative ED cosine theta. Correct. Perfect. Let's see what else do we have. Have this point charge. Remember, this is positive. This is the electric field. Then what happens? Well, if we move toward this positive charge, the voltage, right, increases. The voltage or the potential increases. When we are now with negative charge, right, and we have the electric field, the electric potential increases when you move away from that point charge. Right? Perfect. What else do we have? Well, one more time, we can define also that the potential difference or voltage equals to negative the work done in moving a charge from A to B, divide that work by the total charge. In this case, Q naught. Well, these are the member definitions for voltage potential difference. Okay, work done per unit charge by an external force to move a unit charge from A to B. Okay, perfect. Now let's go to the electron volts. One unit that is used right at this level when we have electrons and charges. All the charges, right, is a very common unit, right? The electron volts. The electron volts, right? When a particle with charge it moves through a potential difference of 1 volt, the change in potential energy is 1 electron volt. Okay, let's see how we can define this. Again, we have that potential difference equals to 1 volt, correct? When we use the definition from here, look, the definition 1 volts is joules per coulombs. Correct, but 1 coulomb, remember, is equals to electrons divided by 1.6 times 10 to the negative 19. Correct. When we send this electrons, we send it to this side, or we multiply by E both sides, right? This is cancelled right here. We have this EV, so 1 EV or 1 electron volt, that's the correct definition. Electron volt is equals to 1.6 times 10 to the negative 19 joules. Okay, great. Okay, now let's go to another topic. It says for point charge with initial 0, potential at infinity. Okay, so this is a charge, positive charge. We have a test charge far away, right? And then we move this positive charge or test charge from that position to a new position closer to the positive charge. Remember, we have to do work because they are positive. If they're approach, right, we have to do work to decrease the distance. Correct? Great. And then what do we have? Well, this is similar to this case. The potential difference is going to be KQ, right? 1 over RA minus 1 over RB. But because RB, right, is a very large distance, long distance, right? this becomes 0. So VB is 0. So what do we have then at the end? What should be the electric potential? The electric potential at this position for this particle? It's going to be equals to KQ divided by RA. Right? That's the electric potential at this position. When we are taking again the gravitational potential N is 0 at infinity, correct? Or the electric potential 0 at infinity. In that case, well, the new position takes the value of KQ divided by R. Okay, perfect. So VA is the work done to bring a test charge, right, from infinity to this position RA. Perfect. Okay, now let's see what happens when we're dealing with potential difference in a uniform electric field. Imagine this is the electric field going to the right. We have a charge, right, at point A, and we move that charge to point B and to point C. Let's go first to point A, correct? And we take this distance or this direction, delta L1. We'll take as a vector 1, 2, and the distance is D. Okay, we take another position C. And let's see what happens when we move the same particle, the same charge particle to position B, and also we can move it to position C. Let's see what is the difference. And the new distance right to position C is delta L2. We have an angle, and these two, right, make an 90 degrees, meets 90 degrees with point with line, let's say point A, right? From A to B and B to C, right, we have a 90 degrees angle. Okay, great. One more time, we define work equals to F delta L cosine theta. And also we've defined the voltage equals to negative work done from A to B divided by the charge. Right. Let's see what happens for part one. Part one is, or case one, when we are going from A to B. What happens then? Well, let's use the definition, correct? And what do we have? This is equals to, remember, work is equals to what? Work is F delta L cosine theta, right? But what is F, right? F is equals to, we use the electric field, correct? Electric field times the charge. But we divided that charge by this charge, and what do we have? We have negative E delta L1, because we are case one, cosine theta 1. Okay, but in this case, at the angle, when you are going from A to B, the angle of this vector, let's say displacement, and the electric field is 0 because these two are parallel. See, delta L1, correct, and the electric field is 0, right? So cosine 0 is 1. I mean, this angle is related to these two quantities, to the angle between E and delta L. Correct, in this case is 0, cosine 0 is 1. Okay, what do we have? Perfect. One more time, this is delta L1. Okay, it's D, and cosine 0 is 1. Okay, perfect. From here, we have that when we substitute the values, voltage is equals to negative ED, right? The electric field, which is constant, times this distance parallel to the electric field. Perfect. Or along the electric field. Okay, great. Part two. One more time, we define the voltage potential difference equals to negative the electric field, which is constant, times delta T2. Now let's take this path, the second path, to point C, cosine theta. Now we have the angle. Okay, perfect. But what do we have? Cosine theta, because we create a triangle, right? Triangle is equals to D divided by delta T2. Perfect. From here, we solve for delta L2 cosine theta, right, which is in this equation, and that is equals to D. Perfect. And then what do we have? We have that one more time, the voltage or potential difference equals to negative ED is the same as before, right? So why? Because one more time, the in this case, the electric potential or potential difference voltage doesn't depend on the path, depends on the initial and final position, right? Because right here, these two are at the same potential, or not. We can define these, or we can conclude these two, that these two points are at the same potential because we have the same voltage, right? So we have some voltage right here, and we have another voltage right here, but these two are the same potential because the difference is the same. In this case, doesn't matter of the path. Correct. So all the points at this line, right, perpendicular to this direction, or perpendicular to the electric field, are at the same potential, right? These are the same potential. And we call this equipotential surface or equipotential line. Perfect. And that's the meaning right here, right? All of these, the lines perpendicular to the electric field are at the same potential. We prove it right here, right? We prove it. You finding the same answer when we change, right, the position, but as long as they are perpendicular, the potential difference is the same. So it means again that these lines perpendicular to the electric field are at the same potential. We can use the same thing for a point charge, right? At the same distance, correct? All these points are at the same potential, Why? Because the difference from here to here, right, is always the same, right? It's always the same value. Okay, great. Let's see, what else do we have? Now let's see what happens when we have a charge conducting sphere. Let's find some graphs. Okay, what happens when we're looking for the electric field on the surface of the charge, where it's gonna be that value, right at the center, right? Inside of the sphere, the electric field is gonna be 0. And outside, of course, it takes the value of the formula that we have for the electric fields when we have point charges. The electric field equals to charge divided by 4 pi epsilon naught r square. Wow, and this is for the electric field. We found this before. What happens to the electric potential? The electric potential, or just potential, what do we have? Well, inside, right, is gonna be constant, and on the surface, it takes the value of charge over 4 pi epsilon naught times the radius. Well, what happens outside? Outside is gonna be, right, as q over 4 pi epsilon naught times r. See the difference? This is divided by r squared, and this is only divided by r. So this decreases faster than in this case. Correct? Great. Perfect. This is more or less how this sphere behaves. Great. And this is for a potential. Now let's go to the potential surfaces. We just mentioned it, right? For point charges. Again, the voltage increases if you're going toward the positive charge, and decreases if you're going away. Correct. You are away, of course, decrease. This is the opposite. Increases if you are going away. Okay, great. You can see this in the figure. Okay, field lines and potential surfaces are always mutual perpendicular. We found it already. Again, this is the potential surfaces for a two positive charges, right? See the behavior. These lines must be perpendicular, right? The equipotential surface must be perpendicular to the electric field line, right? They make a 90 degrees angle. It's the same idea how we can find it, right? In case we're looking for the equipotential surface, correct? We have another example, right? We have a plane and a point charge or a spherical distribution, correct? For any potential surface, the voltage is the same, right? Because otherwise, equipotential. Equi means the same potential, the same potential. So it means that the difference is zero, right? The change is zero. The change in potential area is zero along this line or any line, right? Is perpendicular, correct, to the electric field, correct? Great. The potential change is zero for any displacement perpendicular to the electric field. Okay. So every time we have a change in the perpendicular to electric field, as we saw before, is gonna be zero potential, right? Exactly, or zero potential. We use a voltage. The voltage is, or the change in the potential is zero. Okay, and let's stop right here for this analysis. Let's go back later for this new topic, which is capacitance in dielectric. Okay, great. See you in the next video, part 2 for this chapter. Bye.